purpose and the way how we decided to approach this are such a workshops. For example, today we're going to discuss some basics about system engineering and the space development. On the last SpaceBeer we discussed with the introduction to space technologies, and on the following workshops they will go more into technical details, for example, electronic system, onboard data handling, and so on. So yeah, as I mentioned, today we are continuing with the basics of system engineering. Yeah, I can see some familiar faces, so you maybe already know me. My name is Adam. I work as a technical lead in the YSpace, but also as a project manager in TRL Space Systems. Beside the project management stuff, I also sometimes help with the system engineering stuff. So I'm a bit experienced in this field. Yeah, we are still students in YSpace. We are not really industry-proven professionals, so we are trying to just transfer our current knowledge to you guys. So if you may found any mistakes in presentation or anything like that, don't hesitate and raise your hand and just inform us please about the mistake, and or we try to fix it till next time. Yes, so content of our today workshop. So we are going to start with a basic question: what actually is system engineering? What is a system itself? Then we're going to dive a bit into space project decomposition and definitions. After beer break, we're going to deeply dive into satellite development process from the first idea up to launch. And after second beer break, my dear colleague Christina will take over with her presentation about the satellite operation itself. Yeah, so we can start with a question: what is actually is a system? Yeah, on this slide you can see, for example, system of International Space Station. As you may kind of feel, the word system is kind of intuitive. Basically, you combine multiple spheres or technologies or different subsystems into one to reach one common goal. For example, on ISS, we want to study the effects of a low gravity environment on humans. And to really reach that goal, we need whole this system working. But, for example, the system is not solely connected to space. On this slide you can see the actual system of nuclear power plant. Nicely you can see the inner circle, which is one subsystem, the cooling part, which is another subsystem, and then the electricity generation, so another subsystem. Another nice example could be even our human body. We are really composed of some different subsystems, and together we are one human body system. In reference maybe to system engineering as a job or as a position, you can really maybe compare our general practitioner to system engineer of our body, because he really needs to know kind of basics of everything. He studied like medical school, he's a bit experienced in every field, but he's not the expert. He's general practitioner, and his main goal is to really find out any problems with our body and then send us to really dedicated expert. So keep that in mind. And in this more schematic view, you can see that the system could be composed by really different things, but even like information and past experience and techniques. This is a brief definition of a system by European Space Agency, not really important. But what is kind of important is the first sentence. The system is an integrated set of elements to accomplish a defined objective. So for each system, we need to define objective. What is actually the mission or the goal of the system engineer itself? So system engineer really, it's a multidisciplinary field, as maybe I can reference to this general practitioner example. In technology, you usually have to have bit knowledge from each technology field. For For example, I don't know, if you want to be space or system engineer, you have to have basic understanding of everything about space. But what is really important, you are not really deep dived into one selective subsystem. You have just general overview of everything, but not really dedicated into one thing. And the goal of the system engineering as a technology discipline is to manage a complex system and their development in an efficient, reliable, and cost-effective way. As you may see on the previous slides, the system I described are pretty complex, but up till the mid of past century, usually the things were developed in a way that, okay, we just gonna glue together a bunch of experts from multiple fields. I know they were developing the tanks, for example, so I'm gonna put the experts from the structures, from the engine, and from the weapons together, and they somehow glue together a tank. But when the system became more and more complex, for example, as missiles or satellites, the need for such a new engineering branch really emerged. And from then, we started to really exploit the benefits of system engineering, not just in aerospace technologies, but really in, I would say nowadays, really in every technological field. Using the basics of system engineering I would say, in each development segment, from the software to hardware. You can see some examples of the industries, mainly automotive and healthcare, but really, basically, like everywhere. Yeah, and from now, I'm gonna more refer to space. So I really like this picture here, because it somehow represents the problem I described with the tank from previous example. So you gotta imagine you want to design a spacecraft, but as you may know, the development is kind of segmented into multiple spheres. Let's say there are like control engineers, payload engineers, trajectory, blah, 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 structure, and so on. And if you ask like the structural engineer to develop a spacecraft, we will end up with something like that. If you do the same with the communication engineer, they basically just create a spacecraft full of antennas and transceivers and so on. And the goal of the system engineer is to really combine the knowledge and expertise of every such a group to create one coherent system or technology addressing your objective. Yeah, so that's the main idea. Again, maybe you can the system engineers, you can see them as for example, as architects, but also designers. And it's really important that they do the both. They also need to understand the technology side behind their design, but they also need to be able to design from scratch, from nothing, as for example architects do. Yes. In this figure, actually, it's from European space standards. You can see exact tasks or areas of responsibility of system engineer. Mainly, you can see its analysis, system definition, and then verification and validation of what you produce. We'll touch this more deeply in the following parts of presentation. But what is important on this, that system engineer itself not working like alone. You as a system engineer will be exposed to really a ton of people during your career or during your work on the project. You have to interact with mainly with a project manager, because you are responsible kind of for a whole development process from the technical side. But you also need to discuss a lot of things with production and product assurance, but also with the operations, operation engineering, and so on. But yeah, as I mentioned, we will touch this more deeper in the following slides. Again, on this diagram, you can see the areas of responsibility. Maybe not no term yet, but we'll define it also in the following slides. So system engineer kind of touching the aspects of stakeholder needs, project management stuff, product assurance stuff, but also it's binding connection point to engineering specialist. What I mentioned on slides before, well, there is like communication segment, electronic segment, structure segment, and so on. So it's really like binding, gluing together every necessary part for the development of the product. Now we can follow with a brief, let's say, introduction to space project. But keep in mind that such a structure or division is not purely for a space. Actually, once you're done with your studies and you will end up with some kind of company, it's really good to know or have at least back in the mind some kind of knowledge of project organization, why are multiple team members in a project, what stuff, who taking the responsibilities, and so on. Yeah, so in the beginning, you need an input. You don't usually design just for fun. You design to solve some problem, to improve some technology. And there could be like two types of inputs for you. One is external, from the stakeholder needs, and the second is internal. Internal, you can imagine when your company needs to develop some technology, there is no like external influence, nobody wants from you that, but you as a company want to build your skills, your knowledge, so you decide to design something. So the inputs for the project coming from your company. But most usually, and today we're going to discuss this case, you're solving the stakeholder needs. Actually, who's the stakeholder? It's actually institution, private person, or anybody who owns the money and who is willing to pay you for your work. Stakeholder needs are defined in a document. Usually, it's called statement of work. But what is important, that stakeholder is not usually from the industry and he's not really expert. So he could approach you with some kind of idea. For example, build me an internet relay constellation for a maximum of $5 billion US. In a visualization, you can imagine that as a fuzzy nebula. Really, it's not really clear, like you cannot, from such a definition, you cannot really decompose it to anything. And that, then when the main, or one of the main tasks of the system engineer came to play. And first thing, as a system engineer, you need to define a concept. So you need to read such a statement and build me an internet relay constellation. And you need to define a few concepts, first of all, maybe one, but better is to do like 2 or 3 concepts. So one of the concepts could be constellation of 32 CubeSat serving your data relay needs, and it will cost 4.2 billion. And that's an offer from you, from as a system engineer, from the company to your future stakeholder. So in such a way, you transfer this fuzzy nebula to really some kind of shape. It's not really like clear inside, but the boundaries are pretty much defined. Okay, then the stakeholder or the stakeholder opinion on this, oh yeah, I really like it, I want to continue with you. Then you decompose the project furthermore into sub-units. And then you can even decompose it further, even to smaller units. And then you can, when the project is sufficiently decomposed on small enough, let's say, parts, which you can easily handle and develop, then you can start the development process itself. Then you can start manufacturing, soldering, I don't know, coding, and so on. And when you finish with that, you starting to assemble it again. We'll discuss this philosophy again on the following slides, but keep that in mind, that one of the main goals of the system engineer is to decompose things, logically decompose things to really clear units. Maybe you are familiar with this terminology, maybe not, but usually like the higher goal of almost each project is to earn money and then increase of technology readiness level. Technology readiness level is basically just some kind of statement defined, by, for example, by NASA, actually describe your technology development status. I really like that example with the unicorns. So it ranging from TRL 1, which is basically an idea, what if there were unicorns, up till TRL 9, that you actually design your space unicorn, it's already flown and it's working and so on. So your technology, your space unicorn is really working and you can deploy it anytime. And usually aim of the project is to really increase the TRL, increase. And maybe what is interesting, not aim of all, not in the space, but usually in technology development, usually your goal is not really develop from TRL 2 up till TRL 9, but you go step by step. For example, from TRL 4 till TRL 7. So maybe even if you came up with some kind of project in the space in future and you want to contribute on that project, the final thing you will design may not fly, but it will contribute to technology development. So the guys, or maybe even you, could take over it and further push it to next level. Yep. As we discussed the project inputs, every project needs to have answers for such a question. So what is the benefit, why we are doing it actually, beside money usually. Goal, and the goal need to be really measurable, should be achievable. For example, that I want a relay constellation with data relaying capacity with such a number. Okay, it needs to be something, when you build the data relay constellation, you need to measure how it performs. Then you need to define schedule. It's really different when you have like 2 years or 10 years for development of your stuff. Again, budget, it's really different when you have like 5 billions or 1 million euro. And you need to have human resources, and it's really important. And usually you should answer all these questions before agreement, or before your decision that, okay, I'm going into this project, I want to do it. You should have all the answers in your head or in a paper or somewhere. Now we're gonna discuss the space project decomposition. And basically the main idea is that, okay, let's have an example. For example, there is a NASA or ESA, European Space Agency. As we discussed on a previous workshop, European Space Agency usually want from private companies to build the satellites for their missions. So for example, European Space Agency want to observe, I know, Sun. So they will define the mission, the scientific objectives and so on. And then they will ask the private company to develop it. So in such a moment, the ultimate customer is European Space Agency. And the general, or let's call it, it's usually called prime contractor. It's actually, let's say, your company, Airbus Space and Defense, let's say. So you are the prime contractor of this project. But to really achieve your goals, you don't have the capacity in your company to develop FPGAs, microprocessors, and really this low-level components. Usually you have the capacity to really analyze system, maybe design some structures, but even maybe you want to buy whole subsystems. So you usually go down and dedicate some work to subcontractors. And again, the subcontractors could again dedicate a part of their work to different subcontractors. And it's defined by levels. So the mission levels is European Space Agency. The system level is, for example, me as a spacecraft developer. And then subsystem level, unit level, and we can go down up till the component level. And this kind of tracing is pretty important on the last part of your project when you want to verify that your system working, you want to qualify your satellite, because you need to have elaborated such a whole structure. Because usually when you want to launch your satellite, the launch provider, for example SpaceX, really require the list of components from you and who built the components and the composition of these components. So we really need to have a clear understanding of who is doing what. On such example, yeah, as I mentioned, for example, ESA want to build an observation satellite, so they will define the mission requirements. Then Airbus Space and Defense decide, okay, I can build it, I will do this and this. But, for example, Airbus Space and Defense don't have expertise in battery management or the battery systems. So they, in such a case, became stakeholder to contract with a Voltic company developing the battery system. So the main idea is that the relation between stakeholder and customer, it can be on multiple fields during the development. Yeah, it's pretty nicely visualized on this figure that there is a supplier level and the customer level, and actually you're processing the requirements. When you don't know how to handle the requirements or you don't want to handle them, you will just pass them on the supplier. You will design it over time, and then you will, from the bottom, you will assemble the product and integrate it, verify it, and validate it. So at the end, the customer, the final customer, will receive the product with certain capabilities. Let's now briefly talk about the team composition. Usual one. It don't have to be exactly matching this structure, but it's like usual. For each mission, or maybe nowadays for the private companies, there is some kind of CEO or the Director General with sub-branching, with sub-branches. For us, it's most important the right one with the project management and the system engineering. So as you can see, there could be like business development, public relations, and so on, who taking the care of the project like outside of the technical matter. But there needs to be in every project project manager, and under project manager there is a system engineer who's responsible for the whole like the technology development stuff around your project. He's not usually dealing with finances and contractual details and schedule and so on. Usually just really the technical stuff. Then there is a product assurance. The goal of product assurance in space projects is to really oversee the development from the inside. They usually pinpoint out the risky areas or the problems. Basically the goal is to really develop a product in accordance with the standards and in accordance with the customer needs. So the product assurance taking care of that. And if you are doing the scientific mission, there is a science director with his sub-branches of scientific people. And under the system engineer itself, as we a couple times already touched this topic today, there are like multiple specified engineering branches, subsystem engineers, AIT engineers, operation engineers, and so on. If something is not really clear, just raise your hand. I will try to explain in more easy manner. Again, the project manager, like the description of his role, is actually similar as the project inputs. He needs to take care of answering all these questions. On top of that, he usually communicates to customer, planning the project, evaluating the project risks, and organizing the whole development, let's say, phase, like for example, organization of meetings, reporting, and so on. The main task of the system engineers itself, the technical specification of the system, then architecture of the system, relation between crucial elements of the system. What I'm missing here is the validation and qualification of your product. You need to be also kind of manager because you need to coordinate the development team. And usually, when you develop, as we touched this topic in previous slides, there could be a contractor and customer. And when you're developing something technical, usually the system engineer from the contractor communicate with the system engineer or with a supplier, so they can exchange technical matters of the project. As I briefly touched, the responsibilities of the product assurance. The person need to answer all these questions, and yeah, that's the main goal. A really important person in the project. On following slide, you can see the usual project scheduling or timeline. In our space industry, we usually divide project into phases. Phases from 0 to A are usually for a definition of your needs. You defining the customer inputs, creating the concept, and so on. In phase B, I would say the phase B is most important, because you actually start to develop things. You start to analyze really first iteration of your design. Then when you are somehow satisfied, you can move on to detailed design. You just finish up your design from the phase B. And actually at the end of the phase C, the development usually stops. It really just stops. You order the components, order the manufacturing, then you can assemble the spacecraft, and then you can proceed to qualification and production phase. During this phase, usually testing your product. Okay, you may find out that during the testing there is a fault in a design, and you need to kind of revisit it. But as I mentioned, usually the system engineering or the engineering work stop at phase C. These phases are separated by milestones. Milestone is a really important, let's call it like meeting or set of meetings, when you exchange the current state of the project or your development with your stakeholder. And stakeholder could ask the question of whether your progress is sufficient or not, and you're just presenting your work and trying to find any problems in your development roadmap. Yep. And last slide before the beer time. It's not really important, but I found it pretty interesting. It's the cost over time. I mentioned that the most of the cost is related, or the majority of engineering time is related up till phase C. But you can see the peak after the phase C, when is the production and manufacturing phase. This usually this figure is kind of important when you want to allocate your budget and your money. So you know that in such a phase you need such a budget and so on, because usually you won't receive a full budget for your project from the beginning. Yeah, and now we can have a beer time. Let's say in 15 minutes, so 18:50. Je tomu rozumieť, či ani moc ne?
Dobre to je.
Hej.
No čo si mi, chytáš sa či nie?
No, bolo by lepšie, keby to bolo po slovensky.
Tak ale...
Yeah, guys. So to be on a schedule, we need to continue, and we're gonna continue to actually description of the development phase, from a definition of needs of your mission, through manufacturing up till actually launch of your satellite. And just for information, after me, the Christina will present you basics about the satellite operation itself. Yeah, so the most important thing or the integral part of the satellite development is so-called V model. It's obvious because it's in the shape of the letter, and you're starting with a need. You design the system, and your design system need to have certain capabilities defined by your needs. So as I just mentioned, that we are starting with this customer inputs, stakeholder inputs. We process them to preliminary design. Then we continue with that design to each detail. Then we want to manufacture it, assemble it together, and we can start with a testing phase of our development. So we start with unit testing. We only really testing board by board on a table. Then we integrate everything together, test the functionality, and at the end we want to test the whole system to be sure that in space our spacecraft will be working. So the first step is this kind of elaboration of need of your customer. So usually you're starting with something like concept of operation. On slide in front of you, actually you can see the first concept of operation of YSpace is from the lecture from our last year. The main goal of such a concept of operation is to present your customer how did you understand the topic, and you need to align, you need to show them that what you are proposing, what you are trying to develop is what they actually need. And usually, as I mentioned, they are not from the industry, so it need to be kind of clear, easy to understand. Usually you want to create some kind of diagrams and pictures and this stuff. Yeah, so the main goal is to really show them the concept, the idea. When you hand the concept, you can proceed with the requirements. Yeah, during your career, you will came across this term multiple times. It will haunt you. Yeah, and the main goal of the requirements is to not end up as this. For example, when the customer wanted, sorry, I don't know really term in English for that, but wanted a tire hanging on a tree, and the team totally did not understand the topic, the goal of the product, and they developed something totally different. Yeah, so maybe you can imagine the set of requirements as a recipe. When you're baking the cake, you want add a certain amount of ingredients, and this amount of ingredients should be really precise. For example, 1 tablespoon of sugar and so on. And if you follow the recipe, you will end up with a really tasty cake. But if you do not, or if you change the ingredient, you will end up with something really bad. Yeah, there are some criteria or ways how to write a good requirements. For the aerospace guys, there is this kind of, let's say, saying, just cut the initial velocity. And it refers to the 7 rules. Each requirement needs to be justifiable. So what does that mean? Actually, you don't want to define a requirement out of nothing. You don't want to constrain you based on the reason. For example, such a justification of your requirement could be you define the requirement. Okay, I need a 10 CubeSat. I need the constellation composed of 10 CubeSat. And the justification could be why you need actually the 10, why you don't need like 8 CubeSat. So you need to justify your requirement. It needs to be unique. One requirement describing usually you want one requirement describing only one thing, and you don't want any duplicities in your set of requirements, so on. Singular, it's kind of connected, that your requirement is just for one thing. Maybe you can see it here and on the example. Then traceability, you need such a traceability during the testing, because usually you define the requirements, design the systems, and you testing or validating your system against defined requirements. So you need good traceability. They need to be complete, unambiguous. With tolerances, and you need to be, it's kind of identifiable and traceable is kind of same, and you need to verify. When you define the requirements, you need to kind of think about how I'm going to verify them. You may just review the design, or you maybe need to test actually the requirement. Yeah, and from such a definition and explaining, it sounds pretty easy, but the definition of the requirements is really hard job. And there is a huge difference between the wishes or needs and the requirements. So the wish could be build a big house for my large family. It's really like the fuzzy as the nebula I was mentioning, but the requirements detailedly describing actually what does that mean. The requirements engineering could be divided in these three sections, not really important to elaborate, but the technical requirements are not solely composed by the stakeholder needs, but they are also composed by actually your knowledge, lessons learned of your company, programmatic elements like finances and so on, and environmental or platform constraints. And this is really, really important. Design is based on requirements. There is no justification for designing something one bit better than the requirements dictate. So what does it mean? You don't really want to design something better than the customer wants, because you want to save money, you want to save time, so you just need to design, think till some level of quality. And if requirement describing up till some level, you just want to reach that level. For example, it can refer to this saying that even a child in a kindergarten can build a bridge, but only a civil engineer could build a bridge which is barely standing. And it's really important to have this kind of, let's say, idea in a head, that engineers should really design what they are supposed to. Your design don't have to be a bit better for no reason. The initial part of the development, the satellites, but not just satellites, is really iterative process. And this is called like iteration spiral. And basically, what does it mean? You start with first iteration, you're mostly guessing the first parameters, and then you proceed the whole development, you define the subsystems and so on, and you came up again here. So based on the findings from this part, you can design a new system a bit better. And the first question from my side, I have like two for this workshop, is what is the right amount or the right number of iteration for your project in space? What do you think? One? No sticker for you. Any guesses?
About a 5?
Nope. No.
Enough.
You are closest. Actually, the right amount is one more that you actually have, because you never end up with a perfect system. During the design, you need to, in some stage, you need to just, okay, say, we are done, we are confident enough with our design, we don't really have time or finances or whatever to reiterate it again, so whether it's like 3 iteration or 26 iteration. One more iteration it will be really beneficial, but simply there is no resources for that. So when you define your requirements, alongside of the definition of requirements, you're starting with the functional analysis. And it's really handy thing, because you're starting with the goal of your customer. And for example, your customer wants to take the photo of Earth. So you're starting to think, okay, my satellite will be in space, so what I need for that? So and you as a system engineer will think it, okay, I need to somehow point my satellite, and you can elaborate it further. What you need for the pointing actually, you need somehow power your camera. So you are elaborating further, again for a housing, again for the processing of the photos, because you want to deliver your client not the spacecraft in space, but the client wanted the photos. So you just simply go step by step, define the functions of your system, and this is really handy even during the requirements definition, because you can easily derive the requirements from these functions. On this slide you can see such an example, in our case for mission Kostka. Yeah, so basically you are just going down through the systems. Yep. When you are kind of done with this functional and requirements definition, you can start to build your system, your satellite by blocks. And this is the really important step, because from now we're gonna introduce this kind of subsystems. And like our strategy in the YSpace team is to really have different departments related to subsystems. So that's the idea behind this division. So you will find out that, okay, you need the payload, which is the camera. You need the attitude control system, which is like tilting of the spacecraft in the space. It's like attitude, not altitude. You need power system structures and so on. And from that moment, you can somehow differentiate between each engineering branch, and then you can assign specific engineers for each task. You don't need to deal with a horizon sensor or GPS as system engineer, but you need to really dedicate that area to guys with such expertise. So as I mentioned, in the YSpace team, we have like separate divisions. In following workshops, they will be mostly dedicated to specific division. For example, the next one will be dedicated to electrical system, but for now we're gonna go briefly through the general division in usual space projects from the payload team. As we discussed on a previous workshop, we could have like remote sensing, science, and communication payloads. It doesn't really matter. The goal of this sub-unit in the development team is to take care of a whole development and to be compatible with the rest of the spacecraft. And then, for example, the process data on the ground. Then there is an electrical power system. The project duties like during the development and the subsystem role in the spacecraft itself. So the EPS actually managing the power harness, managing batteries, and also manage the power distribution in your spacecraft. Yeah, you can see the, for example, diagram how it works on the right bottom. AOCS. This is really, I would say, really black magic for the majority of engineers in a space, because it's super hard. A lot of math and calculation and this stuff. But yeah, the main goal is to really, as I mentioned, like tilt your spacecraft, point your spacecraft, and it's necessary for communication, camera positioning, battery charging, because you want to turn your satellites against the sun and recharge your batteries. Next could be the segment of the structures and thermals. So main goal is to really hold everything together, mainly during the start, because the highest loads for the satellites are during the launch itself, but also in a space. It serves, for example, as a common ground point for the electronics. it dissipates or the convect the heat throughout the whole system, so we're taking the care of the thermal needs. Then there is data handling. Data handling subsystem or division usually responsible for a central flight software development, but also all this kind of satellite, let's say, logic. Yeah, you can see, for example, here you can see it's called like star configuration, because there is a command and handling data system, and every subsystem is connected to one single point and looks kind of like a star. But also there could be different configuration when you are using CAN bus, when it's kind of in a round that there is no common controlling unit. Yeah, and the last of this is called like space segment subsystem, is communication system. It's really solely one only connection to your satellite from ground, so it's really super important. Yeah, and the subsystem role is pretty obvious, to transmit and receive data. Actually, you can use such a subsystem in a deep space mission for a positioning of your spacecraft. You can range a distance from your spacecraft. Yep. And there is it's not like subsystem, but it's a segment in a development team, and it's operations. Usually this task will hand the system engineer after he finished the whole system breakdown and definition. He will continue with the operation, and actually it's a logic, a development of a logic of your satellite. You are mostly using this kind of state diagram, state machine diagrams, but also databases. On this picture you can see the operations scheme for the missions. And yeah, so that's also really important. And last major, let's say, segment is a ground segment, and the role of the ground segment is to support your mission from the ground, securing communication, but also managing, for example, data archive, controlling the mission, and so on. What is kind of important when you will be dealing with the space missions in future? The price of ground segment is usually higher than the price of the spacecraft, like satellite itself. So the main idea behind this is to really have a clear understanding that the space project or the space missions are not solely like building of the spacecraft, but it's a building of a whole system around, involving even such things. And when you are like done with your designing and this stuff, you can glue together the whole system, and it's called like physical architecture of your system. And it's just for our presentation. You can see the really like physical connection, like data connection and power connection within each redundant unit. Maybe from the system engineering point of view, what is important on this slide, that each of these individual units is actually like a black box for you. There is a couple of inputs and couple of outputs. You don't really have to deal with what is inside. What is inside is topic of, for example, communication engineer and data handling engineer and so on. But you as a system engineer usually deal with a black box strategy. Yeah, and on this slide you can see such a physical architecture in our case on the mission Kostka. And in compare you can see that physical architecture becoming more, and during the project development, becoming more and more similar to actual physical implementation of the satellite. So you can see the solar panels, you can see the PCB boards with different connections and so on. Yeah, and the last step in this kind of when you're following the V diagram, so we are almost at the bottom. And really important things for the system engineers are analysis. There is a number of different analyses you need to or you may perform, from the thermals to mechanics, electronic or illumination, and maybe when you have some kind of science payload, you need to even simulate that. So when you are like satisfied with your design and you analyze your design, you can really go deep into detailed design. So you implementing everything together, creating the state machine of your satellites, for example, like, drawing the electronic circuits, defining the communication strategies, or creating the CAD model of your product. And in this phase, you are really on the bottom of the V. So you came across all of this, and you are on the bottom. Now you need to manufacture things. And the second quiz question for a free beer. Can you see something weird on this picture, or what is not common?
The satellite is.
Yeah. You want a beer. So as you can see, even during the space development, such a mistake could happen. Actually, the NOAA-19 satellite really just fell from the pallet, and it was really just a human error. And you can see the human error can cause damage for the tens of millions of US dollars. And actually, the reason for this was that between when the shifts in an assemble factory were changing, the first shift forgot to put a special pin securing the satellite on the pallet. And when the next morning, when the next shift came, they just, as usual, moved the pallet, but the whole satellite just fell on the ground, and yeah, they kind of screwed it. Step 7 is a verification of your design. So you somehow assemble it together to one unit, but now you need to verify if it performs as you wish. So as I mentioned, that the set of requirements which we derived, you need to define the test cases. Test case could be one of these, for example, look, write, calculate, or try. Actually, you usually want to really adhere on the first two things, because the cost of the verification increase with this order. So testing itself, for example, the shaking of the satellite or baking it out in the oven, it's really pricey, and you don't want to really do that often. But yeah, regarding to testing and qualification and this stuff, there will be separate workshop. I think it's the last one by Jakub Macejko, so you will find out more about that. Maybe the last slide. So what's the difference between qualification and acceptance? It's kind of important, because when you want to launch your satellite, firstly, there is no way how to fix it in a space when you already launch it. Okay, there was some cases were some cases in the future, but not usually possible. And the second thing, you cannot harm the other satellites in the rockets. Usually you're launching your satellite with a couple of different satellites, and you don't want to harm them with your satellites. So the qualification is really important. The qualification is a process when your product, it could be a subsystem or a whole satellite, undergo such a, for example, temperatures that are not usually common in a space. So your product witnessing the higher loads than it will witness during its operational life. And the aim is to really secure that, okay, your satellite or your component will be working in a space. And then when your product is qualified, you cannot really use it on a spacecraft again. You need to build a copy of it, and such a copy need to be accepted. And acceptance test is quite similar to qualification, but with a much lower loads, or the amplitude is really different. You can see it on this picture. And the main goal of it is to really detect any workmanship errors. So if somebody in the manufacturing did a mistake, so we want to detect that. Yeah. And on this slide, you can see the whole testing sequence. Usually for the satellites and the CubeSat, like really low-cost satellites, we only need to perform the red ones. For the more expensive missions, we also include the yellow ones. And if we're developing something for an international space station, we need to go through the whole cycle. But as I mentioned, more details will be presented by Jakub Macejko on the last workshop about this whole qualification and acceptance campaign. Yeah, and when our satellite is finally qualified and ready, we just need to integrate it. And actually, integration could look in two different ways. When it's a CubeSat thing, you need to put it in this box. It looks like a shoebox. You just stick your CubeSat inside, and at the end of the box is a spring, and in the space it will push the CubeSat out. Or if you're dealing with bigger satellites, you just simply connect it to the top. This is the top of the rocket, and you just simply connect them on the top with a special ring. And actually here you can see that the rest of the rocket is occupied by CubeSat deployers, but the primary payload is different. It's like, I think it's some kind of small sat. And when you are ready, you can finally launch it. And after launch, there is operations, but before the operation itself, there is a beer break. So, yeah, let's say in 10 minutes, possible? 15. Huh? 15? Okay, so 19:30.
Okay, hey guys. Nice to see you. Thank you for being here. I have a presentation dedicated to spacecraft operations. I'm a little bit nervous because it's for the first time I talk to so many people, so please excuse me if I get stuck on some topic. So, before I start, let me introduce myself. My name is Tina, and I am space system engineer here in Brno in TRL Space. And before that, I studied aircraft technologies at Brno University of Defense, and then I continued on master studies on Brno University of Technology. I studied aerospace technologies. In my free time, I really love art and hiking, and I'm also a hobby pilot, even though I am really scared of heights. So the outline is today's presentation is I will introduce you what a spacecraft operation is, what it covers. I will describe you mission operations concept. It also includes ground segments and mission planning. And then I will present you what it looks like when you have a communication window with a satellite. So spacecraft operations. It's quite a broad term. It includes everything what is related to operating a spacecraft. As Adam presented you the development of the satellite, so now you have the toy and you want to play with it. So you have to plan what activities will you do with it, at what time. You also need to prepare operating procedures because there are a lot of people working with a satellite. Also, it includes the infrastructure here on ground. So you have to secure the ground segment like ground stations and mission operations center. You also need supporting equipment because you need to prepare simulations and testing, because if you already have the satellite on orbit, you don't want to screw it up with the first command. So you want to be prepared. And yeah, spacecraft control itself. I want to get you a little bit into the context. So when we have a mission life cycle, we can divide it into phases from 0 to F. On the top line, you have the general term, what the phase covers. And on the bottom, you have the activities which are done during that phase and are related to spacecraft operations. So you start with a phase A, and you define some basic concept of what the mission operations should look like, that you have to secure that the ground stations and estimate how many people you need for the operations and these things. During the phase B, C, and D, you have the development of the satellite, and also you get more into the detail while preparing the ground segment, to preparing the operating procedures, the testing, and preparing the activities and these things. The phase E is like the core of operation, because that's when the operation starts, actually. It starts with the launch, and it terminates during the phase F, which is the disposal. That's when the mission ends. So you also need to dispose not only the spacecraft, but also the ground segment. So it depends on your abilities or your possibilities if you will use the ground segment for another missions, or you will just end it all or sell it. So during the phase E, we can divide it into mission phases. As I said, the operational phase starts with the launch and early orbit phase. That's when the satellite is deployed on the orbit, and all the subsystems are booted, and you also can like deploy the solar panels and these things. Then you go to commissioning phase. That's when you that's when you calibrate your payload, you diagnose the subsystems, and check if everything is like ready for nominal operations. Then there is like the nominal phase. That's when you play with the toy. That's when you operate the satellite, when you perform the activities with the payload. So it depends on the objective of your mission. If you are like taking pictures of the Earth, then you are taking pictures of the Earth and these things. And then you continue with the decommissioning phase. That's when you like end the mission and you deorbit the satellite, or you can move it to graveyard orbit. It depends on your mission. If you are on geostationary orbit, which is located on 35,000 kilometers away from Earth, then you move it on graveyard orbit. If you are located on LEO, which is low Earth orbit, it's like from 160 kilometers to 2,000 kilometers, then you have to deorbit the satellite. It means like mainly that you just load its velocity and you just let it burn in the atmosphere, mostly. Okay, when we are talking about mission operations concept, when you want to operate a satellite, first you have to think about what my mission is doing. What's the purpose of my satellite? You have to think about it's on low Earth orbit, or is it on geostationary orbit, or is it interplanetary probe? Because it defines like frequency and length of communication windows. If you are close to the Earth, then you have a lot of communication windows, but they are quite like short because the satellite is moving quite fast. And then it depends also on, or it influences the number of ground stations. You have to decide, do I want to communicate with the satellite like all day? If yes, then I need a lot of ground stations. If not, okay, I will have just one ground station, but I will have limited time to communicate with it. And if we have, for example, a satellite on geostationary orbit, then it's so far that when we like look at the satellite from ground, it's still on the same place. So we only need one ground station because the satellite, like let's say, doesn't move from point of view from the ground stations. And also, more like the more distance from the Earth, then also the latency is bigger, and so it influences the amount of data you want to download and the latency of commanding the satellite. Other things that influences mission operations. It's our mission objectives and its requirements. So if you have, is your satellite for providing communication service or GPS, or is it a human spaceflight or interplanetary exploration? It all defines like the ground segment, the amount of ground stations, and how many people you need for the operations. If you need just one operator, because your satellite has like is really autonomous, or it's quite dumb and you need an operator to send it every command because it doesn't do anything alone. So then we have a ground segment to establish the communication with the satellite, and we can distinguish three main parts. I will go high level and not go too much to details. So ground segment covers a lot more things, but we will divide it just in three parts. It's facilities, operating personnel, and ground supporting equipment. So we have facilities. It covers mainly ground stations with antennas and also mission control rooms. I will continue with this. But yeah, ground stations. You need the antenna to communicate with the satellite. And this picture, it's from Belgium, from Redu. It's like a meadow with a lot of antennas. But actually, when you have a satellite, you don't need many antennas at one place. You need a lot of antennas around all world to have a lot of communication windows and a lot of time to communicate with the satellite and download the data that you need. Or you have geostationary satellite and you need just one antenna. And let's say that large antennas are beneficial for deep space missions, and also if you want, if you have because there's a big distance from the satellite, and also if you want to download a lot of data, you want to have like high data rates, and you have a satellite on LEO, then you also want to have a big antenna to catch all the data. And they are also used for high frequencies like Q-band and K-bands. And then you need the place where the satellite controller sits and controls the satellites and communicates with it. So these are mission control rooms or mission operations centers. It depends how big it is and how you call it, but yeah. And this is the picture from ESA, from European Space Operations Center. It's in Darmstadt in ESA, in Germany. And yeah, this is the place from which ESA operates all their missions. So during the first phases, like launch, early orbit phase, and during commissioning, the room is full of people communicating with the satellite, and it's quite crowded, and yeah, it must be excited. And I had the pleasure to be there, and they ran a simulation of commissioning phase, and I have to tell you that they have those chairs there. They are super comfortable. But I can imagine that you have so much work that you can even notice. Yeah, and look, that's the picture from this year, and compare it with the picture from 1960, how they control the satellite. It's quite impressive that they did it. Okay, or you can have a mission operations center that looks like this. I know it's not so good, but it's just before that they prohibited taking pictures, so it's quite confidential, so don't tell anyone. It's from Belgium. It's an operations center from which the PROBA satellites are operated, and actually at this center there is nobody, because the satellite has like autonomy. It's so autonomous about its operations, so you don't need anybody to sit on the computer and control it if it does what it should do. So it's it really depends on your mission. If you have like a lot of autonomy, then you need 24-hour controller which is sitting there and doing his job. Okay, then, yeah, it depends how big or complex is your mission. If you have a small satellite, you will probably need just an office with some mission control software and one controller that will handle like everything. Or you have really complex mission, and you will need a lot of people. So you don't want to keep everybody in the same room because it would be like really overcrowded and a little bit chaos. So you can have a lot of rooms dedicated to flight dynamics and flight dynamics team and payload operations, simulation control room, and like for everybody. Okay, and now we have operations team. So basically, you need spacecraft controller, SpaceCoon, that is really like actually sending the commands to the satellite, receiving the data. And then you have a spacecraft operations engineer that is preparing operational procedures and the timeline, who is planning what the activities will the satellite do, and passes it to the controller, which is like executing them. Also, if you have a complex mission, you need some director as always. And you also need engineering support, because if anything goes wrong, you need somebody that understands the satellite very well, who knows the subsystems, how it works, and you need their support and knowledge. Then, as I said, complex missions, you need a lot of people, really big team. Yeah, and ground supporting equipment. You need actually the software which is communicating with the satellite. It is called mission control software. ESA is using SCOS 2000. It's quite robust solutions, and it's like for every mission they customize it, so it can happen that one controller from one mission is not able to control another mission because the software is a little bit different, but yeah. And if you have a smaller mission, some CubeSat or something, you can develop your mission control software yourself, because some, let's say, solutions are available online, like YAMS. It's yet another mission control software, or NASA's solution, OpenMCS. It's like the basic, and you can build up on it. Or you just buy some codes. And also, you need the data storage, because why you have a satellite? That's because you want the data from it. If you have okay, you can provide service like communication and these things. But if you are, let's say, taking pictures or some remote sensing, you need the data. And when you download it from the satellite, you need to store it somewhere. And you need to process the data. So you need the storage. And you also download the telemetry, which is basically the health status of the satellite. It tells you if everything is within limits, if the satellite does not experience any malfunction or something like this. And as I said, you need testing and simulations equipment, because when you finally get the satellite on the orbit, you don't want to screw it up with unprepared personnel. So you need to train them and run simulations so they would be prepared for, like, at the best case, for everything. Because, yeah, orbits are getting crowded more and more, and I think space debris is like a big topic these days. You can be hit by just some trash and or by some not functioning satellite, and yeah, you lost the satellite. Okay, then we have mission planning. When you have prepared your ground segment, then you go to plan the mission, the concrete tasks. So you need to plan what we are doing and when we are doing it. So you prepare a mission timeline. And that's basically, you need to, because at the beginning you have some kind of concept of operations. You know what the satellite will be doing, but now you need it like really minute by minute, what we are doing. And then you need to know how we are doing it. So you are preparing operational procedures. So you see it on the background a little bit. It's like really the checklist of activities, and you as a spacecraft controller, you have to go one by one and like execute the commands and check the telemetry if the parameters are within limits and these things. And as I said, you need not only nominal procedures, but only contingency procedures. You have to be prepared for unexpected events, like that some subsystems stops functioning, or yeah, something like this. And finally, you are prepared, and the satellite is on orbit. You have your operating procedures. The ground stations are ready, so we can communicate with it. And before the communication window with the satellite, which is the moment when the satellite enters the range of the ground station, some things have to be done. Like for example, the ground station have to configure itself and point the antenna toward the direction where it expects the satellite. It's done like few minutes before the acquisition of signal. Then the satellite appears, and either the satellite or the ground station sends something like hello message that, hey, I'm here, let's talk. So they create a communication link, and the communication can start. First minute of the communication window can be unreliable. So you have to wait a little bit, and yeah. And then you can download the data. It's called downlink. You download the telemetry, housekeeping data, you download payload data, everything what you have like measured, took photos, or you made experiments, so you want the results, so you downlink it. And then you uplink the commands. You want to ensure that the satellite will know what it will do in next hours or days. So yeah, and it depends on the mission. If you are located on low Earth orbit, the communication window can last, I don't know, 10 minutes, let's say, every 90 minutes. Or it's a little bit less, because not every time you catch the satellite, and sometimes it can last like 2 minutes or a few seconds. Or if you are on geostationary orbit, then you can have the communication window all day. 1 minute before the loss of signal, it's again unreliable signal. So and then the signal, it's loss of signal. And after the pass, the ground station goes back to its default setting and is prepared for another passes. And you, as a spacecraft operator, you analyze the data that you have received and adjust the procedures or the timeline that you have planned before, so it would be prepared for next pass. And yeah, that's all from my side, and if you have any questions, please ask. And thank you for your attention.
I would like to thank Adam and Christina for the great presentations. I hope you enjoyed it. Soon there's going to be a slide that you're going to see that you can look into our website and look at our missions and what we are working on. And you can also fill out the feedback for today's session so that you can give us more information that we can improve for the next time. So I would like to briefly introduce YSpace for those who don't know. YSpace is a team that's focused on the development of the first Czech student satellite. However, that's not all that we do. We have other activities and other stuff and other projects that you can join. So if you are thinking about joining, if you're not already a part of YSpace, you can fill out a form on our website yspace.cz or yspace.but.cz, and you can become a part of the team. And I would also like to invite all the heads of the different subsections here so that we can have a talk with everyone that's already part of the team and who's already thinking about being part of the team, and we can also introduce the different subsections. Again, please give a big round of applause to Christina and to Adam for guys want to come? Okay. You can, yeah, put that. Okay. So let's start from the left. This is Jiří. He's responsible for software in our team, and we work closely
Together?
Software. Me and Jiří work together closely because I'm the head of electrical subsystem. This is Adam. He's the technical leader of our team, and he's responsible for the overall overseeing of the mission Koska, which is the supposed to be the first Czech student satellite. However, there's a small competition from CTU, but we are glad that they already woke up from their nap and they already started doing something. We're glad that we've inspired them to do something. So this is Zuzana. She's responsible for the social media, and she's the reason why you all are here. So she's amazing for posting all the stuff and giving.
I would say not only social media, but general like presentation of.
Everything everything about the team. She's responsible for that. In case anyone's interested in helping her in expanding the YSpace audience, she's the person to talk to. And Marek, together with Kuba, they are the heads of together with Maciej, of course, the heads of the development of the entire structure of the satellite. So that's the CAD systems, that's the simulations and everything. So if you guys want to work on that, they are the guys to talk to. Then there's David and Alex, and they are people responsible for the communications and the transmitters and receivers and all that takes care with talking to the future first Czech satellite. And then next there's Vašek, who's the oldest team member of YSpace. And he's basically our mentor in terms of mechanical subsystems. He has great experience, and he's been also developing BUT Cube as sort of a project on the university. So he's the most experienced with us.
Yeah, I would say the main idea behind this round of introduction is that the team members, maybe you already know that I created the pool in our Microsoft Teams, but due to some issues with the Microsoft Teams, unfortunately I can't really see the result, the names behind the votes. So we need to figure out a new way how to reach to you. For example, I'm responsible for system engineering, so if you want to help us, or we want to be allocated in this segment, please, like after this round of interview, came to me and we'll discuss the next steps. We will decide on like regular meetings and so on. And it's case for each division. So if you're interested in the software, go talk to Jiří. If you are interested in the electronics, go talk to Dominic. System engineering, me and Vašek. Marketing, Zuzana, but also me, whatever. Marek, Kuba, and tall guy Maťo. Structures and thermals, and communication, Alex and David. Yeah, maybe if you were listening closely, currently lacking the expertise in AOCS, which is attitude determination and control, but that's not a problem for us because our satellite Kostka won't have such a system, so it's okay.
Very simple.
Yeah. So really, please reach to us so we can plan the next steps.
Okay, go ahead. If you're not already a part and you want to be a part, please make sure to fill out the red button on the website so that we have your contact information. Just click on the red button. I know they always say don't, but click on the red button and fill it out so that we can put you in our Microsoft Teams platform where all the communication happens.
Yeah, and to secure our division into field, each of the, let's say, division leaders will write something in the separate channel on Microsoft Teams, and please just put a, I don't know, like or emoji on that message, so we somehow know who is actually in the branch, because we didn't told that it's going to be so complicated, but it's kind of is complicated to really separate the people. Yeah, and we by the end of this week we should have like clear project roadmap up till end of the this school year. So yeah, we'll like to present it to you, but on the as we said, like on this subsystem level, to really separate the tasks and so on. Yeah, so.
Yeah, grab a beer. We'll be here, and
Wow. And for the rest,
You're such a poet.
enjoy the, I don't know, the beer and the stuff, I don't know, culture or whatever, up till 10.
yeah, that's
Yeah,
we need to leave at 10 because it's not a pub, it's actually it's like student organization. So
There are people sitting up there, so.
yeah.
yeah.
Sorry. Yeah. That's all from our side for today, and really, and don't really forget to